Hello and welcome to another IAEI News Live. My name is Thomas Dimitrovich, and today's topic is on surge protection, the fundamentals of surge. And we're going to dig into some NEC code requirements. We're going to have to work on understand what surge is, what surge solutions are, all that great stuff. And you know what? It all starts now. All right, so I can't believe it's Tuesday already, and it is halfway through March. We're almost through the first quarter of 2022. I don't know where the time is going, but it's going. You know, last week I was just with Jody Wages down at the Electrical Safety Workshop. I'm sorry. Yes, at the Electrical Safety Workshop, IEEE's Electrical Safety Workshop. We were in Jacksonville, Florida, and we had a great week. We talked electrical safety all week, and maybe one day I'll do a summary on what that event was about and how the IAEI is working to bring more engineers into the fold, because the IAEI is not just about electrical inspections or electricians. It's not just about applying the National Electrical Code in a facility. It's about electrical safety, and electrical safety transcends those individual topics. So, and trades. So Jody Wages was down there, and we did a quick interview. You have to check that out as well. But okay, so surge. You know, surge is one of those, in my opinion, surge is one of those areas of discussion that brings a little mystery to the table. And the reason I say that is because we can't see surge. We can't see when a transient event occurs in a power distribution system. And I think there's confusion out there on what is a surge, what is an overvoltage, what is an undervoltage. The discussion around voltage is an interesting one. So chat it up. You know, if you have any questions, please submit the questions. Chat in the chat. Make comments on this video. I'll be looking at it and following up and trying to answer those as we go through in the future videos, because this is a recorded session. I just want to make sure it's clear. This is a recorded session that I recorded before I left for another training session. I'm doing 70E this week. So those little gray boxes that we put on, it could be a little black box. It could be, it's some small little device that we install on power systems, or it could be that technology that's in that multi-tap strip where we go, why is this one more expensive? Well, it has surge protection, and you just sit there and wonder, what's it doing, right? Because we can't see transient voltages. We can't see the voltage sine wave. And the impact of surge events may not be immediate. You know, we're so used to talking about short circuit events that demonstrate themselves through catastrophic failure of a piece of equipment, that unintended rapid disassembly. But you wonder, when a surge happens, it may not produce anything that's evident. Yet, you'll have a piece of equipment that, over a long period of time, all of a sudden decides to fail. You take it back to the manufacturer of that product. They look at they'll open it up and they'll say, "Oh, we see what happened. It was the motherboard failed, or there's a trace on this circuit board that's failed." And you wonder, how could that have happened? Could it have been heat? Could it have been a lot of different things? And it just may be the result of surge events over and over and over and over. A good example of how small events can all accumulate is that bar of soap that you put under a dropping water. If you took a bar of soap and put it in the sink and you had a leaky faucet and it just dripped every now and then, if you left that bar of soap under that dripping water long enough, the bar of soap would be eroded away to nothing. That's an example of long-term impact of surge events on equipment within a power distribution system. You need the longevity. You need that device to be there performing for a long period of time, because that's how surge events can exhibit themselves and the damage that they can do over a period of time. The surge events that occur that produce immediate catastrophic failure are typically from your lightning events, and we would typically call those it's a lightning surge, or you would need a different level of protection than what we're talking about right now. That lightning protection, that very large impulse due to a direct hit, I don't know much that can protect you from that. And what do we do there? We move into grounding, and we move into creating those shields so the current has paths to flow around, say, a structure, and hopefully not through a structure. But there's not much you can do for a direct lightning hit. But we can protect ourselves from the long term of events such as nearby lightning events, or even far away lightning events that impact the transient voltages in the power distribution system. But as we're going to learn today, there are a lot of internal effects on the power distribution. There are a lot of internally generated surge events that impact the internal systems in our power distribution systems. So get ready, get your code books out. Mine's on the floor here. I'll have to get it soon. And I will, and I have another book here. I've got an emerald book, the IEEE emerald book, and it just happens to be green. Powering and grounding sensitive electronic equipment. Another great reference for you. We're gonna have a lot of these types of discussions because we're talking surge fundamentals. All right, let's get going. So what is a surge? We're talking about high amplitude but short duration overvoltages. Now, this is where some people get a little confused because of that word overvoltage. They'll say all overvoltages are surges and all surges are overvoltages. We're going to get to that. That's not true. The surge can be a positive or negative polarity. Why could I say that? Well, you think about a sine wave. A sine wave has a positive half cycle and a negative half cycle, right? So I can have a surge in voltage on the positive side of that half cycle or on the negative side of that half circle. And surges can be large. They can be, there's another term you're going to see. Transient. So I use the word transient there. That's another term that has been used over the years in industry to reference and talk about surge events. So, and we're going to talk a little bit about that history as well, but that terminology transient is an important piece of the puzzle. In fact, years ago, what did we call it? We called them transient voltage surge suppression. TVSS. We've gotten away from that. Now we just call them a surge protective device. But in my opinion, that term transient is an important part of what we're talking about, because that is what helps us understand the difference between an overvoltage and a surge event. Now, these, from an amplitude perspective, and I believe we have some sine waves to show you. But these transient events can be up to greater than 2 times the system RMS voltage. Now, if you think about RMS as a root mean square, then remember you have a peak voltage, and then the transient event, the worst case would be a transient event at the peak of your sine wave, right? That would go up and over in a transient event. That would be your worst case scenario. And what prevents you from that worst case? Statistics, I would say. You don't really know. There's nothing that says, I'm going to wait to that downslope. I'm going to wait for the zero crossing. I'm going to wait to it to be negative. And I'm going to avoid the peaks when I create a transient on your system, because it's all about when you flip the switch, when that motor started, when that breaker tripped, when the utility capacitors decided to ring in. Nothing dictates when a surge event is going to occur other than when the surge event occurs. Now, noise. This is another, noise is, there's another thing to remember about a surge event. It rides the sine wave. It's not overlaying on top of the sine wave. And again, we're going to see some pictures, but remember, the transient event will be on your sine wave, voltage sine wave. It's not going to be another event, another voltage suppressed onto the system. It's a part of the voltage. Now, noise, if you've ever seen a sine wave that had a lot of, it didn't have a nice straight line. It was a lot of little squiggly lines on top. That's what we call noise. Noise is something that rides on top of a system. It could be interferences, various frequencies riding on top of your voltage sine wave. But the magnitude of noise is much less than a transient surge event. That noise can be translated into various frequencies. If you broke that sine wave out into all of the different frequencies, you would see what is making up that voltage sine wave. Those higher frequencies have other effects that have harmonic concerns. And that too is a long-term issue in a power system, but a completely different discussion. What we're talking about are short duration overvoltages that occur. And again, a surge event can be thousands of volts. Now, that image over there on the far end, that shows you what I meant by, now that's a worst case scenario, because the transient event is right at the peak of my voltage sine wave. Those are the worst case. And that's a positive one. And then the other down here is your negative transient. And that's 2 transient events in succession. Now, the duration of those can be they are very short. You can zoom in on that one transient event up there at the top, and you'll see the microseconds that it occurs. And that very large, abrupt change in voltage will drive a very large up change in current as well, because that voltage is being impressed upon a load. And when you impact voltage, there's another important aspect, and I've got a one-line diagram to help describe this. But when you impact voltage, you impact a much broader range of equipment in your power distribution system. Think about what I just said. A voltage transient that comes in from the utility may impose this type of an event at the service equipment. And voltage is across everything in the power system. So that transient event is not just hitting a load, it's hitting anything connected to that piece of equipment. It raises that voltage for anything connected to that equipment. That is an important piece of the puzzle. So, a current event. We get into a lot of this discussion. This discussion usually, when we talk voltage impact and current impact, is typically like a power quality discussion. We're talking about, in some cases, you might have harmonic content. You might have events that impact current to a specific load. I could have a harmonic distortion on current going to a drive, and that's current distortion. Now, you could make the argument that a current distortion will impact the voltage, which then impacts a broader range. True, that's true. But a current distortion driven by a load will impact that branch circuit itself more so than the entire distribution system. This type of an event of a transient voltage nature impacts a much broader footprint and much more equipment, which is why we'll tier the protection. And you might say, well, of transient voltage, depending upon where you put placing the surge protective devices or transient voltage devices that throughout the power distribution system, someone would say, well, that's an overkill. Not necessarily. Okay, there are plans and approaches to provide a good level of protection for all equipment, and it rarely involves placing one surge protective device at the service equipment. Okay, and if you think about what you're seeing here, you have this transient voltage that's up pretty high in the system. Okay, say this is at your service equipment. Say this event right here is at your service equipment. If you have a transient voltage device that clips that off at that point, making that go away, you're still left with a transient event over that sine wave that will propel itself, that will be seen downstream. And downstream devices might be able to clip these at lower values. So that clamping capability is an important aspect to say I'm cutting off. So my system, technically, we consider it as clamping that voltage peak, but technically we're shunting current to ground, right? We're moving that current around that it's generating as well. So trying to simplify to help you understand what's going on. Sometimes you get into trouble trying to oversimplify, but suffice it to say, what our goals are is to deal with that massive piece of damage delivery that and I'm trying to do that with these little boxes that might have two indicating lights on it, tell you it's still working, and you say, well, how do I know it's working? It's hard. It's hard to demonstrate it, but I do have a couple of videos that hopefully will help you understand that. So a transient. Now, if I go to, I'm getting this from IEEE standard 1100, which is the recommended practice for powering and grounding sensitive electronic equipment. And they call it the Emerald Book. So, what a transient is a subcycle disturbance. A subcycle, what do we mean by subcycle? What we're showing on this screen is a subcycle. So what is one cycle? So here is a half cycle. Here is one cycle. So from this value, from this point in time to this point in time is one cycle. Let's see if I can write this. 1 cycle. So that is 1 cycle. I'm sorry. Yep. So you have typically 2 half cycles. That's 1 half cycle. Let me clear this up because that's wrong. Erase all. I know if I got to draw a line this way, that helps you. Might help you see it a little bit more, a little better. And this is your. So that's your axis. So 1 cycle would be right here. There's a half cycle. So 1 cycle is from here to here, or from that point to that point. That is 1 cycle. It's easier sometimes to look at it from a complete sine wave and not a cosine, right? So if I draw this line and I say, there's the beginning of my cycle, there's the end of my cycle. Here is the beginning of my cycle, there is the end of my cycle. Okay, so depends on where you start on the sine wave. And that's what, and really this event I'm showing at the peak, that's the worst case. That event could also happen somewhere in here or in here, which would have a lower peak value because it's not running off the top of the sine wave. That makes sense. All right, so a subcycle is within 1 cycle in an AC waveform that is evidenced by a sharp, brief discontinuity of the waveform. Okay, that is a sharp discontinuity of the waveform. Would you agree? It could be of either polarity, positive or negative, and may be additive to or subtractive from the nominal waveform. Now, the subtraction is typically referenced as a notch that has different impacts on a power distribution system. But what I'm going to show you now are a few terms that you need to understand because technically all of these are voltage events. You have overvoltage, you have voltage swells, you have voltage notches, you have voltage transients. Now, a notch is a disturbance lasting less than a half cycle, which is initially of opposite polarity than the waveform and is subtractive from the normal waveform. Includes complete loss of voltage for up to a half cycle. That is a notch. I got a little picture of that here. And that's an ugly looking waveform, but those are notches. What you'll see, let's try to zoom in. Okay, that is a notch that occurs, and it could go down to 0 volts, all the way down to this line here. Those are notches. So you have a notch, which is a voltage event as well. So then you have an overvoltage. Now, overvoltage, here's what this is what IEEE standard 1159 says. When used to describe a specific type of long duration variation, refers to an RMS increase in the AC voltage at the power frequency for a period of time greater than 1 minute. Typical values are 1.1 per unit to 1.2 per unit. So, when I say overvoltage, this is what we typically will reference. If I tell you I had an overvoltage, if you were an engineer and you learned from books like the IEEE Emerald book, and you studied transient events, and you studied other notches and whatnot, because you're looking at sensitive electronic equipment, your perspective of overvoltage is what I'm showing here. Now think about it. It's an RMS increase in voltage, and root means square. It's not a transient event. It's not a subcycle event. An overvoltage is typically greater than 1 minute, and it's an RMS value. We call it an overvoltage. Now, I could the way I think the National Electrical Code, and I'm talking about 2020 code, if I think about what we did in this book, we created a new article in the 2020 Code Edition in Chapter 2. And we called it overvoltage protection. Now, Article 242, the scope of it provides the general requirements, installation requirements, and connection requirements for overvoltage protection and overvoltage protective devices. Part 2 covers surge protective devices, permanently installed on premises wiring systems, if not more than 1,000 volts nominal, while Part 3 covers surge arresters, permanently installed on premises wiring systems over 1,000 volts. Now, I don't think we define overvoltage in the code. I'm going to just double check. Oh, Chapter 1. We don't. Now, we do define overcurrent. You have overvoltage and you have overcurrent. Overcurrent is any current in excess of the rated current of equipment or the ampacity of conductor. It may result from overload, short circuit, or ground faults. Now, I could argue that an overvoltage is any voltage in excess of the rated voltage of equipment or the voltage ratings of conductors. And it may result from a voltage swell, a voltage transient, or RMS increases of voltage at the power frequency for a period of time greater than 1 minute, right? So I could say that a transient voltage event is an overvoltage, but an overvoltage is not always a transient voltage event. Just like I can say a short circuit is an overcurrent, but not all overcurrents are short circuit events. Let's talk a little bit more. Swell. What's a voltage swell? This is another formal term. It's an increase in RMS voltage or current at the power frequency for durations from 0.5 cycles, a half cycle, to 1 minute. Typical values are 1.1 per unit to 1.8 per unit. So now we're talking cycles. Remember, an overvoltage, we have RMS voltage changes. RMS, root mean square, means I need multiple cycles. And this is how IEEE defines it, not how the NEC defines it. So if you're an electrical engineer, this is how you were taught. For a period of time greater than 1 minute. That is what we call an overvoltage. A voltage swell is from a half cycle to 1 minute. And we already talked about transient, right? I'm almost positive we talked about transients. Remember what a transient was? A subcycle disturbance in the AC waveform. So you have a subcycle, less than 1 cycle in a transient. You have from a half cycle to 1 minute as a swell. And then you have from 1 minute and greater in time period as an overvoltage. This is how the Institute of Electrical and Electronic Engineers defines these terms. And the code has introduced Article 242 called overvoltage protection. And in my mind, I got to reconcile that. I have to think, this is how I was taught. I know what an overvoltage is. And when we had this discussion at the table, because there were public inputs and comments seeking to change surge protection device to an over voltage protection device. And those around the table in panel 10 said, no, that does not make sense. Why? Because of these terms, and these terms have been used for years. So you have a group of engineers and others who have been taught voltage protection and taught that this is what an overvoltage is. This is what a voltage swell is. This is what a voltage transient is. And this is what a voltage notch is, right? So I think Article 242 is going to have a journey. It's going to take a journey. And it could be that the vision of Article 242 is to provide reasons to have over voltage protection, which is an RMS type of long duration. Think about the impact to equipment where you have a RMS increase in voltage for a long duration above the rated voltage of equipment. That's a problem. Transient voltage surge suppressor, a surge protective device, whichever term you want to use, whichever vintage you are in yourself, knowledge-wise. Remember, we use surge protective device as your terminology today. Applying that is not going to help you in an over voltage situation, which could also damage equipment considerably. So in the new Article 242 in the 2020 code speaks to over voltage protection. And we have surge protective devices in here, and we have also surge arresters, two different types of solutions for two different problems in the National Electrical Code. Stay tuned, I think, for 242, because I think there might be some more changes coming down the pike, but I don't know. All right. We talked about a swell. Now, this was that earlier discussion I had. Remember, when I have a transient voltage event from the utility, it propagates its ways down through the entire power distribution system. And obviously, it will be less in magnitude, dampened, so to speak, the further down in the system that we get. Now, keep in mind, too, a transient event can occur at this motor and propagate itself. It can be a transient voltage event can occur because of switching anywhere in this power distribution system. It doesn't always come from the utility. I don't know. This is just an example. So if I have a normal operation, I've got a voltage sine wave operating and behaving itself. I don't have any operation of the transient device. But if I do have a transient event, I could have a kaboom. And you've got to love the kaboom, right? That's that now we say kaboom. And this is, I love and I hate this slide. I love and I hate both these slides. Because the reason is that transient event may not result in a kaboom. That kaboom may come 5, 6, 7 years from now on a piece of equipment that should have lasted 30, 40, 50 years. And then you have a premature failure of equipment. And you go to the manufacturer and you say, why did this occur? What happened? And the manufacturer takes it apart and says, well, you had a failure of the motherboard and it could have been surge. And you'll say, yeah, okay, I get it. It's surge. So you're just saying that just to get out of the warranty, right? but it's true. Because these surge events, I remember the bar of soap. That's a great analogy to help people understand the long-term effects of a transient. You still have a bar of soap. There's first event, the second drop, the third drop. You could sit there all day and watch it and say, I'm not seeing any impact on this bar of soap. Come back 5 years later and that bar of soap is gone. Why? Because you eroded it over time. It's the same thing with these transient events. The kaboom may not occur today when that transient event occurs. Multiple hits over a long period of time will send you back to Best Buy or whatever store you go to or went to buy that. I almost said VCR, to buy your DVR these days, right? Or the new flat screen TV, or if you're an industrial facility, that control panel or machinery. These events will take a toll on the power distribution system over a long period of time. And an overcurrent protective device. This is the inside of a fuse. That's your fuse element. Do you know what opens a fuse? Current. And lots of it. Do you know what trips a breaker? A thermomagnetic circuit breaker especially. Current. And lots of it in a long duration. These transient voltages events do not produce enough current that lasts a long enough time to open an overcurrent protective device. So a circuit breaker or a fuse is not going to provide you with that protection. Unless, now there are some circuit breakers out there where they've integrated surge into the packaging of the circuit breaker itself. So when it does double duty. Okay, there are manufacturers who have a circuit breaker, say a 60 amp circuit breaker that you might have on a hot water tank, and it's got built-in surge protection. And provide surge protection not just for the hot water tank, but for the entire facility because it's attached to the bus. But you're not getting it because of the 60 amp circuit breaker itself. There are receptacles that have built-in surge protection. There are power strips, multi-tap units that have surge protection built into them. So a surge protective device limits that transient voltage by diverting or limiting the surge current. That's what it does, basically. That's why I was saying it's hard to describe how that gets done. But it does what it does when it does it because it's diverting and limiting that current, that surge current. Let's just keep going. So you have different types of surge solutions out there. Type 1 is permanently connected, intended for installation between the secondary of the service transformer and the line side of the service disconnecting. So a type 1 device is installed on the line side of your service overcurrent protective device. A type 2 is on the load side of your service disconnect overcurrent device. A type 3 is at the point of utilization. I would say a good example of a type 3 would be like a surge strip or a receptacle that has your surge protection built in. It's at the point of utilization. Maybe it's in a cord. And then your type 4 is a component that you might find in, say, an industrial control panel, so to speak, that's built into, it's built on the board. Those are DIN rail mounted typically. They might be a part of an assembly, maybe on a motherboard, etc. Those are your type 4s. So your type 1s you'll find on the line side. Your type 4 you'll find. So your type 1 is before that service disconnect. Your type 2 is after the service disconnect. You'll see it in service equipment. Your type 3s would be at your point of utilization at your equipment. You'll see these like, I don't know, in data centers down close to the computers and things of that nature. And then your type 4s are recognized for OEM applications. So those are built into the products themselves. You wouldn't be installing those as an electrician or electrical contractor external. They would be built in. Now, you might be replacing something that's built in. There are units, surge protective devices, that once they have given their life to protect the equipment, you can replace them. And those are UL recognized for OEM, other equipment manufacturer applications. And UL 1449 is the standard for surge protective devices. That is the standard that governs the development of those protective devices. I still got my Christmas mug. I love this mug. Anyway, then the question is, why? All right. Now the question is, why do we provide surge protection? Surge protective devices can present a solution to prevent outages and equipment replacement. Extend the longevity of your equipment. This is an example, real world example. Lightning strike entered a metals fabricating facility, destroyed $20,000 worth of control panels, electrical infrastructure, and Cisco infrastructure. Loss of data system also cost 11 days of production. That's a real world example. $20,000 worth of control panels. How many of us have lost TVs, phones, DVDs, DVRs, whatever it is, computers, due to surge? That cost. Think about this. So a lot of people will say, well, you've got to find the safety, right? But the National Electrical Code has the only thing the National Electrical Code deals with is safety. And I would argue, I beg to differ. I really do. And why? I go back to Article 90. 90.1. What is the purpose? Practical safeguarding. The purpose of this code is the practical safeguarding of persons and property. Persons and property from hazards arising from the use of electricity. So if I have significant loss of property, that's another reason for the National Electrical Code. It's not just about, I don't have to say those control panels that were lost, well, I have to tie a death to it. No, I do not have to tie a death to it for it to be substantiated in the National Electrical Code. Why? Because read 90.1, persons and property, not persons and property that leads to hurting persons. Okay? The National Electrical Code, if I show a significant loss of equipment, millions and millions of dollars of loss due to surge, that is a justification for putting a surge requirement in the code. And it doesn't have to have a daggone thing to do with saving a life. If I can save our industry, if I can save across the United States, all homeowners combined, billions of dollars by putting surge protective devices in, I have justified the existence of surge in the National Electrical Code. Doesn't just have to be life safety. Persons and property. Don't forget about that. Estimated downtime attributed to power quality issues, 55% in 2010, 47%. US 80. Look at this number: $80 billion a year due to power-related problems. 80 billion. It's a lot of money. That's a lot of money that could be diverted into other areas, in my opinion. Where surge comes from: 20% external, lightning, capacitor switching, short circuit events. 80% internal, load switching, short circuits, but you never thought about that, right? Load switching, imaging equipment, variable frequency drives, arc welders, lighting dimmers. You can generate transient events from within the facility that impact other areas. Here's an example of capacitor switch. We call it a ring wave, right? So that is a capacitor switching transient. I was called out a while ago to California. We had a facility. This is in the early days of arc fault circuit interrupters. I'm talking branch feeder AFCIs. And we had a issue where the circuit breaker was tripping in a complex. And what was unique about this application, which we had never seen before, was I had an entire complex going at like 6 o'clock in the morning at 10 o'clock at night. It wasn't just one person. It was a whole group of homes. And so we fly out to that application, and actually it was a new home development, and they put us up in a because we were trying to capture these waveforms, and they put us up in one of the demo homes or whatever, that you would tour. So we slept in there, and we had our sleeping bags, the whole bit. So we put all of our equipment up, and we captured the event in the morning, and we captured the event in the evening, and it was a ring wave. And the issue was, because it was such a new development, the ring wave was very pronounced. And what was occurring were power strips, those multi-tap units that were on, that you put on your TV and whatnot, that have voltage protection in it. Those units were designed in a way that they shunted current not to a neutral, but to the equipment grounding conductor. The equipment grounding conductor. So they were surge devices. Remember what we said earlier, a surge device will shunt that current. And they were shunting it to the equipment grounding conductor instead of the neutral. If it had gone to the neutral, everything would have been fine. But those early ground fault, those early AFCIs, and the GFCI breakers were tripping as well, which was really unique in these applications as well. Those surge strips were presenting a ground fault for a pretty good duration, because this you look at that sine wave and that ring wave, and this isn't from that event, but it was very similar. It was much more pronounced. And it was a longer transient event that was occurring, and for a couple of reasons. There weren't enough homes that were brought onto these transformers and whatnot, and there wasn't a lot of load, etc. So in any case, that transient event was causing enough current. We had 30 milliamp ground fault protection of equipment on those early branch feeder AFCI devices. These are the branch feeder, not the combination types. And it was, and this was, I believe, even before the National Electrical Code formally adopted AFCIs. It was just in our test units. And we would do things like that. You install these products out there in clusters of homes. You work with the builder, you work with a contractor, and we want to put this technology in, and you get the feedback and whatnot before the code adopts stuff. But anyway, we learned that we learned a couple of things. One, we had to put a slight delay in our ground fault protection, which was, remember, it was GFPE, not GFCI. We had to put a slight delay to make sure that we ran through these abnormal events, but also the surge strips were shunting to ground and not neutral, and they should have been shunting to neutral. So that drove a standards change or discussions at the standards in that regard to say, where are you putting these? Where are you dumping these currents? Because you have the objectionable current rules within the National Electrical Code, and one could argue, is this an objectionable current that you're now? These events happen twice a day, and then any types of surge event that would happen throughout the day was putting these transient currents on the equipment grounding conductor as well, and it was a real demonstration that this community needed surge protection because of these transient events. Now, I'm sure once the homes all were put in and we started to load the system up, the dampening effect of this transient voltage probably did occur over time. We never went back and measured after the, at the existing location, what the events look like down the road, but suffice it to say, it was a significant effect that was probably, if without protection, slowly damaging electronic equipment within these homes. 80% of surge events are internally generated, cause of internal surge events, large motors turning on or off, imaging equipment, copiers, lasers, medical imaging, breakers opening and closing, variable frequency drives, arc welders. There's a lot of different reasons, but 80% come internally and not just from external events like lightning or capacitor switching. The RMS voltage excess 150%. You can have a transient from motor starting and stopping. Closing your breakers, contacts, you're separating, you're creating an event by abruptly stopping the flow of current, drawing an arc, and you might get a change in that current fluctuation, which drives the voltage fluctuation. We call that current chopping. Now, Dan Carnevale is going to give us an example from Eaton of a lack of surge protection, and then what surge protection does for you. But remember, you typically don't see what a surge protective device is doing for you. I might try to play this. Oh, no, I won't. All right, here we go. Hold on. You got to take the pen off. There it is.
We're going to use a 7,000 volt, 3,000 amp transient to simulate lightning striking near your home or facility. We're going to do this demonstration with a standard incandescent light bulb. Think about if that was your HD TV at home, or if that was the PLC controlling your plant. We're using Eaton Corporation's Power Expert 8000 meter to record these events. All right,
so the next one is another example of when surge is actually put in place.
Now we're going to do the same demonstration with surge protection. With surge protection, the voltage gets clamped to 352 volts, protecting the load.
Remember that first peak, that first transient that he showed was 4967. Okay, this is your trace of your voltage that light bulb basically saw. And what the surge protective device did was limited to only 352 volts. Now, you can provide, as you go down in the power distribution system, the various levels, that 352 might still smoke a motherboard of a computer. Think about that. That 52, which is clamped for this light bulb, doesn't damage the light bulb, but a sensitive electronic device that's small, dainty, plugged in, 352 will smoke it in a heartbeat. Surge protection happens in layers. That's why we layer the surge protection to keep knocking that voltage down to something that the electronic equipment can manage. That's what we're doing with surge protective device, and that's why we layer the protection. You just don't put it in one spot and forget it. No, you have it at the service, and then you place it in other locations in your power distribution system because you're continuously knocking down the voltage. You're getting it into a manageable chunk, and then you are slowly knocking it down. Now let's take a look at the NEC. 230, Article 230, service entrance, right? We made some changes in 230. 230.82 tells us what can be connected to the supply side. And 230.82 you have instrument transformers, you have conductors used to supply management devices, circuits, fire pumps, you have solar photovoltaic systems, control circuits for power operable service disconnecting means, you have ground fault protection systems or type 2 surge protective devices where installed as part of listed equipment if suitable overcurrent protection and disconnecting means are provided. So 230.82 tells us I can put this on the line side of my service overcurrent protective device. And then 230.94, relative location of overcurrent device and other service equipment. The overcurrent device shall protect all circuits and devices. There is an exception. Drum roll, please. High impedance shunt circuits, surge arresters, type 1, surge protective devices. Where do we say type 1 would be? On the line side. Surge protective capacitors and instrument transformers, current and voltage, shall be permitted to be connected and installed on the supply side of the service disconnecting means as permitted by 230.82. So 230.94, this is relative location of overcurrent device and other service equipment. And then you don't treat those as a service overcurrent protective device, even though they're on the line side. If they're serving these solutions, they're not treated as a service overcurrent protective device. 708. This was 708.20. Let's just take a look at 708.20. We're bouncing around, Tom. 708.20, 708, 701, 702, 705, 706. Jiminy Crickets. 708.20 is titled Sources of Power, and D. Now remember, 708 is your critical operation power systems. Now this went in, trying to remember when, I think it was 2011 code. But that surge protective devices, what it says is surge protection devices shall be provided at all facility distribution voltage levels. In the 14 code, Article 700, 700.8 was added, surge protection. So 700.8 was new in the 14 code. A listed SPD shall be installed in or on all emergency systems, switchboards, and panel boards. The big question that came out there is, why do I need to put them in every one of them? And I hope you understand the layering effect that surges can occur within a power distribution system at any one of those levels, and we want surge protection at each of these panels inside of a Article 700 system because we're protecting sensitive equipment that are used for life safety. But again, I don't need them just for life safety. In the 14 code, Article 694, which is on wind electrical systems, 694.7D was new. No, it wasn't new. 694.7D was not new in that version of the code. I don't have my 17 book. I'm going to look in the 14 book. I don't know where my 17 book went. But I'm going to look in the 17. 694.7D. 694.7D. 690. This is when I was in the tab. This was when I was into tabs, man. Oh, they were the greatest thing since apple pie. But you know what I learned was I don't have patience to put them on. 694.7D. 694 is wind. There was no 694. Well, actually, wait. 694. 692. 694.7. 7 is installation. And D, surge protective devices. So it's been in there a while. I think what happened here was Article 285 in the 2020 code. We had to reference a different section. That was the only change that we made. Article 242 instead of Article 285. This is the 14 code. So surge has been required in Article 694 for a little bit now. 620.51E. What happened in 620? That's your elevators, people movers. 620.51. D. 620.51 ABC. D. Identification and signs. E. E, not D. E. Okay, it was in the 2020 code. Where any of the disconnecting means in 620.51 has been designated as supplying an emergency system load, a legally required system load, or a critical operation power system load, listed surge protection shall be provided. So they added the legally required system load or a critical operation power system. They added those two references. Surge got a little love in the 2017. 645.18. What's 645.18? 645, I know is IT. 645. Where's 645? Here we go. Surge protection for critical operation data systems. Listed surge protection shall be provided for critical operation data systems. That's pretty vague. I think that's pretty vague. Don't you think it should be provided for critical operation data systems? What does that mean? I think it needs to get a little love in the next cycle. That's what I think. Well, this is 17 code. So 670, that was when it was put in. So in the 17, they put that in. And the only change they made in the 2020 code was that it has to be listed. Big change. Has to be listed. 670.6. That's the other thing. I'm looking at the 17 changes, and I'm reading out of a 2020 book, so got to keep me honest there. 670.6. Now, 2020 made some changes here too, but this was new for the 17 code. Industrial machinery with safety interlock control devices not effectively protected from voltage surges on the incoming supply circuit shall have surge protection installed. So this is safety interlock control devices. 695.15. 695.15. Mark your books. Tab them. Because these will escape you if you don't remember. 695.15. 695.15. Surge protection. A listed surge protection device shall be installed in or on the fire pump controller. This was added in the 17 code based upon a study conducted by the NFPA Fire Research Foundation. And you can get those studies. You can get those studies. If you just go to the Research Foundation website. So you'd have to go and you can Google half of these or search half of these. We're using any search engine that you use. Now in 230.67, so this is the 2020 version of the NEC, and they did expand surge requirements in Article 230. And my book is just falling apart. Article 230. Let's take a look. 240. 230.67. 230.67. The whole section is new. Surge protective device. All services supplying dwelling units shall be provided with a surge protective device. This is in 230.67A. That's A. All services supplying dwelling units shall be provided with a surge protective device. The location. The SPD shall be integral part of the service equipment or shall be located immediately adjacent thereto. And there is an exception. If so the exception basically is like when you have that meter stack or meter center outside, there's panel boards inside in each of the residences. You can put them at each of those panel board locations and you don't have to put it out there on the meter centers. So you can put it at the first levels distribution downstream. Now I will say location of the SPD is critical, as close to the bus as possible. You want to keep those lead lengths very short. Very important to do that. And then the replacement types should be SPD shell types 1 or type 2. Type 1 or type 2. And then replacements. Where service equipment is replaced, all of the requirements of this section shall apply. So they're picking up replacements. All very important. Now, another thing that was new in the 2020 code was they created a new Article 242. Keep in mind, the only thing they did was consolidate all of the requirements. The changes that we're going to probably see in 242 are going to come for the 2023 code cycle. So stay tuned there. There are some requirements that are some provisions of Article 242, which if you look at 242, the scope tells us a lot, as it always does. Okay. The scope of Article 242. This article provides the general requirements, installation requirements, and connection requirements for overvoltage protection and overvoltage protective devices. Part 2 covers surge protective devices permanently installed on premises wiring systems not more than 1,000 volts nominal, while Part 3 covers surge arresters permanently installed on premises wiring systems over 1,000 volts nominal. So you have the generic requirements, and you still have those requirements in each of those articles that we just talked about, which, electric machinery, elevators and control panels, Article 700, Article 708 types of systems. Those are still telling you where you need to put them. 242 tells you the details of what you need to put and where. And I'll just give you an overview of how surge Article 242 is laid out. We're not going to get into the details of reading through Article 242. You can go back and do that yourself. We have Part 1 is your general requirements. This is your scope and your relation to other articles. And 242.2 tells us, it's actually 242.3. So it's not 242.2, it is 242.3. And I'll tell you, see, it was easy. I changed it. So that's Part 1. Part 2 are surge protective devices, 1,000 volts or less. You have where you're not permitted to use those, 242.6. These are on ungrounded systems, impedance grounded systems, or corner grounded delta systems, unless specifically for use on those systems. Again, voltage is a consideration in properly applying these surge protective devices. It tells you that they have to be listed. So any SPD, any surge protective device out there must be a listed device. In the short circuit current rating, these devices have short circuit current ratings. They have to have a short circuit current rating that exceeds the available fault current at that location. Then they have 242.12.1 or 12. You have type 1, type 2, type 3, and type 4. And they tell you where each of those are permitted to be installed and how they're to be installed. So type 1, supply side of the service, disconnect. And then at the service, grounded, when installed in services, type 1 SPD shall be connected to one of the following: a grounded service conductor, grounded electrode conductor, a grounding electrode conductor, grounding electrode for the service equipment grounding terminal in the service equipment. You got type 2 SPDs, and then you have type 3 SPDs and type 4. And then it tells you the number required. Where used at a point on the circuit, the SPD shall be connected to each ungrounded conductor. And that's in 242.820. Right? See, these are all in Part 2. You have the number required. You have the location. permitted to be located indoors or outdoors. And you have the routing of connections or connections. Then you have the connection itself. And they reference other sections in the code. In conductor size, the line and ground conductor shall be small, shall not be smaller than a number 14 or a number 12. So, and then there's dot 30, connection between conductors. So they're going through each of these technology, and that was under 1,000 volts. Now you're over 1,000 volts. Where you're not permitted, the surge arrestor selection, the number required, location, routing, and connection. So this 242 pulled together all of the other requirements that you find in other locations within the National Electrical Code and put them into one spot. But again, you're still going to have to go to like 700 tell you when you need to install it. 230, when you need to install it. 708, when you need to install it. In other areas that we already talked about. All right, so that's sort of an introduction / overview of the requirements that can be found in the National Electrical Code. You got a reference here in the Emerald Book. It's IEEE Standard 1100. And I'm sure you have other reference materials out there that you may know of that are of interest for you. But remember, surge is a solution that will protect equipment over a period of time. Surges are overvoltage, but not all overvoltages are surges. We've got swells, we've got other types of considerations. And I think we did some damage on surge. All right, so that's all I had to say about surge. Hopefully you are all a member of the IAEI, and hopefully you are all subscribing to the channel here on IAEI. Make sure you get out to the YouTube channel. If you're watching this on any other platform, please get out to our YouTube channel and subscribe. We need to get those numbers up. Hopefully this little tech talk enlightened you a little bit more on this topic of surge and surge protective devices. All right. Thanks for joining IAEI News Live. Thanks for what you do for electrical safety. Thank you for what you do for the electrical industry. Thanks for being a subscriber to this channel. If you are, I look forward to connecting with all of you further. And thanks for your membership in IAEI. Don't forget, membership has its value. Take care, stay safe, and remember, please, stay healthy.